Welcome to Lab 1 Charge Tapes by Isaiah Tanon. As far as an introduction, the purpose of this lab was to generate a hands-on understanding of how neutral matter can gain a charge and how we can calculate different aspects of that charge to find electric field, the force it impacts other charges with, and approximately how many electrons it is deficient or excess in. Specifically, we used clear Scotch tape to demonstrate this. A couple fundamental principles we need to understand is that neutral matter can gain a charge through friction, again losing or gaining electrons. Things in static equilibrium have a net force of 0 because there is no acceleration, and the electric force requires a charge of both points, and we of course need to understand that like charges repel and opposite charges attract. An experimental overview: we used 4 pieces of tape total, 2 were bases and 2 were ripped off of the bases. This charges the tapes with like charges, and through a known charge, specifically plastic pen rubbed into hair, which we know to be negative, we could see how the tape interacted. In this case, it was attractive, and therefore the tape is positively charged. We took 2 of the like charged tapes, set them up vertically, and measured the displacement of the top tape. Here's a visual of that. Again, the top tape is tape B, and we used the bottom tape, tape A, to push it upwards against the force of gravity. Here's a model of that, the green arrow representing the force of electricity and the red arrow representing the force of gravity. Some basic measurements for the tape. The tape length was 20 centimeters, the tape width was 1.5 centimeters, the tape mass 0.2 grams, and the total top tape displacement was about 2.5 centimeters. All the calculations done later were done with standard units, which you can see in the parentheses. Calculating the force of electricity that tape A produces on tape B, we're considering tape B to be the system, so it has 2 forces, electricity and gravity. First, we found the force of gravity on tape B using its mass and the universal gravity and the negative 9.81 meters per second squared. And then we used Newton's second law, knowing it's in static equilibrium, and we just took the negative of the force of electricity. The magnitude of the force of gravity is equal to the magnitude of the force of electricity. For calculating charge, we know that tape A produces a charge to tape B, or they're both charged the same, and we were able to multiply the force tape A has on tape B by the displacement of tape B squared, and then divide by epsilon 0, and lastly take the square root, and that will show us the charge of each tape. And calculating the electron to atom ratio, since our tape is positive, we know that we are electron deficient, there are electrons missing. We're able to divide the charge of the tape by the charge of an electron, which tells the amount of electrons we're missing, and then find the number of atoms by taking the area of the tape and divide it by the atom length squared. And then we just took the ratio of those numbers to find our ratio. Here's where all my actual computations went into, my glow script code. We can see the force of electricity calculation, the charge calculation, number of electrons, number of atoms, and the ratio. And all those results are pictured here. Again, here's the model where we assumed the tapes are point charges. The red arrow is gravity, green arrow is force of electricity. And we see that the charge is positive or deficient in electrons, and we can see how many electrons are on each tape, or how many atoms are on each tape. As far as assumptions we made throughout the experiment which create room for error, we ignored air resistance and external factors on tape B, which can alter the calculation for the force of gravity, which alters the electric force calculation, and which changes all the other calculations as well. We also treated each tape as a point charge. Instead of as a real piece of matter, we treated it as a single compressed point in space, which isn't exactly how all its atoms and electrons are laid out, but it was the only way we could make this experiment truly possible. As far as additional questions, what if the electrons and protons had opposite charges? Visually, nothing would happen. All our calculations would have opposite signs, but really nothing would happen in the real world because it is in equilibrium and relies on both charges being opposite. And why is it important to handle the charged tapes as little as possible? The more you handle the charged tapes, the more the tape is going to lose its charge and regain the electrons that it needs to return to its ground energy state, because all objects are wanting to return to that low energy state rather than being in a charged state when it's not their natural orientation. That is the end.